Hello everyone, I'm Shungoku Mazawa from Tokyo Institute of Technology in Japan. Today, I'm going to talk about ExtraFerns fully parallel ensemble learning technique with non-greedy yet minimal memory access training. Let's begin. Here is the outline of my talk. In recent years, many people use AI applications daily thanks to the development of machine learning. There are two forms of AI applications: the current mainstream cloud AI and the rarely used edge AI. What's the difference between them? These are the schematic diagrams. In the inference phase, both run the models on the edge devices. But in the training phase, they are different from each other. In the training phase, first, the edge devices get the training data. The edge AI trains directly on the edge devices and generates models. But cloud AI throws the training data to the cloud servers. Then the cloud servers train the models and send back to the edge devices. This is the difference between cloud AI and edge AI. In cloud AI, this data transmission causes a number of issues such as network bandwidth, data privacy, energy consumption, and so on. In contrast, edge AI does not have these problems and is a very reasonable form for various applications. Then, why does cloud AI with such problems remain mainstream? The answer is because it is difficult to train on the edge with poor computational resources. In general, the training process requires more computational resources than the inference process. So how can we achieve training on the edge? The solution to this problem is a training method that is suitable for edge environments with features such as low power consumption, low memory requirement, and low computational cost. Neural networks are currently used in many situations due to their high accuracy, but they require a lot of computational resources for training, so they are not suitable for edge training. On the other hand, decision forests are not fancy machine learning algorithms now, but still outperform neural networks for tabular data. Compared with neural networks, they need only a few parameters and a small amount of computation, so they are suitable for training on edges. The decision tree is one of the most popular models used in statistical machine learning. It is a machine learning model that has the branching conditions of the internal nodes and the class labels or values of the leaf nodes. Decision trees are rarely used by themselves and are often used as base learners in ensemble methods to achieve high accuracy. Decision tree ensembles are well-known methods with high accuracy and robustness, which combines many weak learners of decision trees. They generate multiple decision trees in training and integrate results from them in inference. Random forest is a popular method of decision tree ensembles. Let's look at the generation of a decision tree in random forest. Suppose we train a dataset with 7 instances such as this. First, random forest assigns all the data to the root node, and next it selects the attributes of the training data randomly. These points represent the data points. The random forest fully searches for the best division threshold among these 3 random attributes. Theta 1 on x7 is the optimal threshold, so the splitting condition becomes the attributes of x7 and the threshold of theta 1. It then divides the 7 instances into 3 and 4 and repeats the process recursively. And for the ensemble, random forest makes a lot of trees in this way. Next, let's look at extra trees, an extension of random forest. Extra trees randomly select attribute and threshold pairs. Then it selects the best one among them as the splitting condition. Extra trees save a lot of computational costs compared to random forest by choosing random thresholds. However, since these methods require reading random data attributes for each node creation, they require a lot of access to the training data memory. This is a cause of a high power consumption because accessing off-chip memory where data is stored accounts for most power consumption. Is there any model that can solve this problem? For this problem, we turned to the Fern structure. Fern is a decision tree with a unique structure sharing an identical internal node in each depth. So Ferns can be considered Boolean functions using the internal node's outcomes as arguments. The Fern structure has no dependency between nodes. Therefore, it is unnecessary to split data from the root node in sequence, like a decision tree, and each node can be split data in parallel. Also, since the number of internal nodes is only the number of depths, the number of data readings for the generation of internal nodes is considerably less than the decision tree. These advantages mean that Fern is a good model for edge computing. Next, I will introduce the ensemble methods using Fern. Random Ferns is an ensemble method for image classification that uses Fern as a base runner. Random Ferns sets the branching condition of the internal nodes of each Fern as a comparison of the intensity between two randomly selected pixels of the image. Next, R-Ferns is a generalization of random Ferns to be used for normal tabular data. R-Ferns randomly selects attribute and threshold pairs like extra trees and uses them as branching conditions for each Fern node. But there are problems with these methods as well. The first is that they are very memory intensive. In this figure, the Fern's depth is 3, in which case 8 leaf nodes are generated. So, since the number of leaf nodes increases exponentially with depth in Fern, it consumes a lot of memory to store those leaf nodes. And then, the weakness of R-Ferns is that, while R-Ferns is very simple and fast to process, R-Ferns is less accurate than decision tree ensembles. Fern structure is very simpler than decision tree, so high randomness is likely to reduce accuracy. As we have seen, each of the conventional algorithms has its own disadvantages in running on the edge, such as memory access or memory space or accuracy. So we propose a new running method, ExtraFerns, based on conventional algorithms that compensate for these shortcomings. Next, I will introduce the ExtraFerns algorithm. ExtraFerns is an ensemble method that uses Ferns as base runners for classification. In the generation of a Fern in ExtraFerns, first, ExtraFerns generates nodes with random thresholds and attributes for branching conditions like extra trees. Second, ExtraFerns builds a Fern in the same manner with random Ferns. In these processes, ExtraFerns reduces the number of memory access and computation by using the node generation method with extra trees and the Fern structure of random Ferns. So ExtraFerns is based on extra trees and random Ferns, and the name comes from these two methods. However, like R-Ferns, this random generation is difficult to achieve a high degree of inference accuracy, so ExtraFerns performs additional processing. Third, ExtraFerns conduct parallel threshold optimization to achieve high accuracy. Instead of the greedy search for optimizing each node's prediction performance like random forest, ExtraFerns searches the best thresholds for optimizing the entire Fern's prediction performance. And finally, ExtraFerns calculates each leaf node's probability distribution similarly with random Ferns and R-Ferns. The distinct difference is that ExtraFerns does not use decrep priors, allowing ExtraFerns to reduce more than 80% of memory requirements for storing leaf nodes. And for the ensemble, ExtraFerns makes a lot of ferns in this way. Next, I will describe this parallel threshold optimization and leaf probability calculation in detail. First, I will describe the target function of parallel threshold optimization. These are the functions of information gain and gene impurity used as the splitting criterion in decision tree training. Decision tree training divides the data at the point where the gain function is maximal. From these functions, we define the target function of the threshold optimization in ExtraFerns. We call this part of the function the purity, which is derived from the gene impurity. The biggest difference between the gain function of the decision tree is the underlying part. While the decision tree calculates the gene impurity for only the left and right child nodes and tries to maximize the gain, ExtraFerns calculates the purity of the entire leaf nodes and tries to maximize it. This indicates that ExtraFerns is a non-greedy optimization that tries to optimize the entire leaf nodes. Next, I will describe the algorithm for threshold optimization. First, the data is pre-quantized to 8 bits. Next, we select a node to be the target of the optimization. Then we fix the thresholds for all other nodes and shift the target threshold from the current threshold to a range of R, and look for the threshold that maximizes the objective function. And this optimization is done at the same time for other thresholds. For the target node of the optimization, the other node's thresholds are fixed, so changes in the other thresholds at the same time don't affect that node. Then, once all nodes have done this process in parallel, we update them simultaneously. This is repeated in a U epoch. This animation shows a threshold optimization for training a fern on an iris dataset. The graph displays two attributes of the iris dataset. The color of each data point represents a class, and the line represents a threshold. As you can see from this figure, the thresholds move at the same time. Now I finish explaining the threshold optimization, and then I will explain the leaf probability calculation. ExtraFerns calculates the leaf probability after threshold optimization. To calculate the leaf probability, ExtraFerns assign the training data to leaf nodes. This is the training data, and the colors represent the classes, and F represents the number of the leaf. First, the internal nodes test the data and assign data to the leaves. Then, the leaf node counts the number of assigned data in each class. After finishing assigning all the data, ExtraFerns compute this probability for each leaf. Now, let's calculate this probability normally like this. In the inference phase, Fern ensembles estimates the class by multiplying the probability obtained from each fern, according to semi-naive phase theory. If the inference data is assigned to this leaf, the output of this fern is this probability, but it is 0 for both classes. This is a zero frequency problem in naive phase. To prevent this problem, random ferns and R ferns use a Dirichlet distribution and set the probability of all the leaves to a non-zero value. They store these all leaves probability, so memory usage is very large in random ferns and R ferns. In ExtraFerns, to solve the zero frequency problem, the probability of empty leaves is set to 1 for all classes. ExtraFerns calculates the log probability and does not hold empty leaves probability because an empty leaves log probability is 0. Experimental results show that more than 80% of the nodes can be empty, so the ExtraFerns achieve more than 80% memory reduction compared to the random ferns and R-ferns. Now, I finish explaining the leaf probability calculation, and then I show the evaluation results of ExtraFerns. We compared ExtraFerns with random forest, extra trees, and R-ferns in terms of accuracy, memory space, and memory access. In the experiments, we set the number of trees or ferns to 1000 and the other parameters to default. Each result is an average of 10 trials. This table shows the dataset we used in this evaluation. First, I show the results of the accuracy comparison. In comparing ExtraFerns with R-ferns, ExtraFerns has significantly higher accuracy thanks to threshold optimization. In comparing ExtraFerns with random forests and extra trees, ExtraFerns is inferior, but the accuracy difference is within 5% at the most. Next, I show the results of the memory space comparison. For comparison, we consider only the internal and leaf nodes of the dominant factors occupying memory space in each method. We measured the number of leaf nodes and estimated the amount of memory from them. First, I show a good case. In the MNIST dataset case, the ExtraFerns used the least amount of memory even when the depth was large. Next, I show a bad case. In the Kuzushiji MNIST case, the memory consumption of ExtraFerns was the largest for any depth because ExtraFerns generated more leaf nodes than the other methods. Here are the cases for all datasets. When the depth is 15, ExtraFerns requires an equivalent or a smaller memory size with other methods. But when the depth is 25, ExtraFerns requires more memory space than others due to a large number of leaf nodes. And finally, we estimate the number of fetched train data from off-chip memory as off-chip memory access when we set depth to 15. We estimated the off-chip memory access for datasets with large memory sizes. From the table, random forests and extra trees required 23.4 and 24.3 times more training data. Therefore, ExtraFerns required only 4.3% and 4.1% of chip memory access for random forests and extra trees. Since off-chip memory access accounts for most power consumption, ExtraFerns are much more low power consumption than random forests and extra trees. In this presentation, I introduced an edge-oriented machine learning algorithm called ExtraFerns. The ExtraFerns is based on extra trees and random ferns. In training a fern in ExtraFerns, first, ExtraFerns generate nodes with random pairs of attributes and thresholds, like extra trees. Next, ExtraFerns builds a fern in the same manner as random ferns. Then, ExtraFerns conduct parallel threshold optimization to achieve high accuracy. And finally, ExtraFerns calculate the probability of the leaf nodes. At that time, ignoring the empty leaves and making the leaves sparse reduced the memory usage. And I showed the results of the ExtraFerns evaluation. In terms of accuracy, ExtraFerns were considerably higher than R-ferns, and one step short of random forests and extra trees. In terms of memory space, ExtraFerns used more memory space for depth than the other methods. In terms of memory access, ExtraFerns required only 4.3% and 4.1% of chip memory access for random forests and extra trees. That's all for my presentation. Thank you.